So, Mike, are you happy to hit record? Yep, you've just done that.
Good.
Thank you. Thank you. So I'd just like to acknowledge that I'm joining you and those of us at the Statewide Biobank are joining you from the land of the Gadigal people of the Eora Nation, and we pay our respects to elders past, present and emerging, and we recognise their very important connection to and care for country. So it is really fantastic to be welcoming Professor Malcolm Pradhan today, and yeah, Malcolm. He's actually we learn about Malcolm's work because one of my colleagues here at the Statewide Biobank is going to an AI in health course at the University of Sydney, and he already heard Malcolm present and said he was really very impressive. So we're really looking forward to hearing you, because it is also, it's such a popular topic, generative AI at the moment, and it's actually not that easy to find speakers because these people are very in demand. So I think we're extremely fortunate to have Malcolm joining us today.
Thank you.
So Malcolm, I'll just give a bit of background. So Malcolm has a career in health economics and AI spanning over 25 years.
Informatics, health informatics.
Health informatics, sorry. And he's an adjunct professor of digital health at the University of Sydney. He holds a medical degree from the University of Adelaide and also a PhD in medical informatics from Stanford University in clinical AI. So Malcolm has co-founded the Alcidion Group, which is an ASX-listed health IT company, and he served as CMO working on products for the Australian, New Zealand and UK markets in patient flow, EMR, virtual care and also clinical decision support. So he currently consults on AI and go-to-market strategies to healthcare organisations and startups around the world, and his focus is on how to adopt AI. We just might ask people to go on mute if you could, please. That's great. Yep. So he's currently consulting on how to adopt AI safely and responsibly by organisations. And I think if people who have been following the use of generative AI over the past year, we all recognise that that's really a key challenge. So we're very grateful that Malcolm can join us. We're really looking forward to your talk. Thank you so much.
Thank you very much, Jennifer, and thank you everyone for attending today. So I'll go at a pretty snappy pace and hopefully just pick up questions later. There's quite a few concepts to cover, and hopefully the goal of today is to really understand what's changed in the whole AI space. Why is it sort of blown up? What is the underlying technology, just to give you some intuition around it, so you can better judge the products that are getting pushed to market very, very quickly, because there's so much money going into this whole area. And so we're going to learn a whole bunch of things like prompts and tokens and foundation models and fine tuning and things like that, which is part of the core elements of all this technology that's going on, and really trying to look at the impact on clinical, on how to integrate this into clinical work and what it means for governance as well. So what I'm going to do is pretty quickly cover the general area of this technology called transformers. So when we talk about ChatGPT, which I'm sure everyone has heard of at this point and hopefully had a bit of a play with, it's composed of two components. One is the GPT part, which stands for Generative Pre-trained Transformers, and transformer is the underlying neural network model that is the basis for this. And chat means that the model has been fine-tuned to interact with people, and it's also undergone alignment to make it less racist and sexist and biased in general. So that's kind of what this technology is about. It's this underlying transformer technology that's been adapted to interact with us. And while we're going to get really caught up in this whole generative AI side, it's worth noting that artificial intelligence as a field has been around for a long time. It comprises many different methods and techniques, from rule-based systems right through to semantic knowledge networks to machine learning. Machine learning is a part of that. So machine learning the other side was really having to be manually constructed. Machine learning learns from data, and a subset of that is neural networks, which is based on deep learning technology, and a subset of that is the transformers. So that's so while everyone's obsessing about the generative side, as we'll discuss later, there are a wide range of techniques. Not everything needs to be done through a generative model. So what happened some years ago is around 2011 is that neural deep learning networks made a bit of a breakthrough, let's say, and this was with image recognition. So back in 2011, the error rate on image recognition was around 25 or 26%. And within 1 year, using deep learning, it went down to just about 15%. And then it achieved better than human performance by 2015. So what's happened is that by giving models large volumes of data and allowing them to learn from that, we found that for image recognition, at least, it could get better than human performance. And we found that, in breast cancer diagnosis, retinal lesions, skin melanomas. And then there was a whole lot of stuff done on video for, say, surgical interventions and so forth, and even some attempts with non-image data as well. Although the big breakthroughs really came through, and that came through a whole variety of some improvements in techniques, the rise of graphical GPUs or graphical processing units. Which allowed all these matrix multiplications to occur much faster. And so while it was amazing, this is going back quite a few, 12, 13 years now, we're only just finding these products hitting the market now because it was discovered that these models were quite brittle. While they were really good at understanding pixel data, so they would pick up, say, a tree, saying, yes, it's rapeseed, but if you added some slight perturbations onto the image, you could get it to flip it, with 95% confidence. So this is saying, yes, it's a J, but then you give it a bit of some pixel perturbations and suddenly it'll say it's something else completely. And to the point where you could have single pixel attacks on the images and get it to flip from saying this is a horse to a frog, with just adding the pixel. Yeah, there's a lot of theory on where to place the pixel. But the point is that people realize that these things were quite brittle. They understand pixels, but didn't have a knowledge of the world and understand, well, what a horse is and actually. So to do that, prior to transformers, you had to manually create knowledge bases. You had to give the computer facts. You had to link them up manually. And that worked quite well for certain areas. Watson, IBM Watson at the time, when it beat Jeopardy, was really a manually constructed system. But it didn't scale. We couldn't really get it to grow. And so what happened a few years ago was that transformers are a technology that take large data sets and can incorporate knowledge and reasoning automatically from data. Right, so that's new and that's big, because previously machine learning was good at predictive tasks and classification tasks, but it didn't reason about these things. So, for example, you can try this with your different ChatGPT or whatever model that you're playing with. Explain the importance of HDL to LDL ratio in a real world analogy with someone with low healthcare literacy, and it will go along and create this analogy about garbage trucks picking up good trucks picking up garbage and bad ones throwing it down. You need to have more good ones than bad ones, otherwise the street gets clogged up. So what's really fascinating is you give it this prompt and it will generate this text, and it's not just stuff that it's seen before. It can combine information and knowledge from the text that it's been fed and trained on. And you would have heard that these things learn by predicting the next word, if you like. And so the transformer architecture, the way that you wire together the neural network, was developed in 2017 by Google, really for language translation from one language to another. And the key thing here is it learns facts and concepts So not just raw facts, but it generalizes facts into concepts and then can reason about them. And so how does it do that? By learning the next word. And intuitively, we can think about it as saying, well, if it's predicting the next word and you're feeding this model, I went for a walk with my dog, but I stopped at a coffee shop because I had a pain in my blank, and it's going to predict the next word. So any of these things are kind of up for grabs, right? Latte, pet, leg, chest, like it could say, I had a pain in my cappuccino or whatever. So what prevents it from choosing that? So to do this well, it turns out you need to actually have a lot of implicit knowledge about the world, and these models then start to realize that to predict the next word, you need to have a lot of concepts and context. So living things can have pain. Pain causes reduced mobility. Chest pain is more serious than leg pain. So maybe it's, if you're stopping at a coffee shop, and etc. So these concepts are built up in the network, and through these parameters that it learns, these weights. And that's been the really surprising thing, is how effective this technique has been. So what do I mean by weights and parameters? So some of you may be familiar with say a regression model, where you just have inputs like age and weight, and then you have a formula, linear or logistic formula that just combines these, says, okay, the age multiplied by some weight, and then you add that up across there, and it gives you some risk score, for example. So it's just adding that. That's kind of all these models do, except what happens, that score, rather than just calculating a risk, if it hits a threshold, will fire an activation into the next layer of the network. And so these neural networks are like billions of regression models stacked up on each other. And so the weights represent the knowledge and the reasoning in these models. So it's, we can't point at a node though and say, oh, that's where renal impairment is stored, because this knowledge is distributed in a strange way right through these networks. So parameters turn out to be quite important. So when Google published the Attention is All You Need paper talking about transformers in 2017, they came up with BERT, which was really used for their search, as you expect from Google, as a search model. It had 340 million parameters. So a typical regression model might have like 10 parameters or 12 or something like that. This had a 340 million. Then OpenAI came out with GPT-2 at the time at 1.5 billion. And I don't know if you remember, but they said, oh, we're not going to release it publicly because it's too dangerous, hilariously at the time. And since then, it kind of went nuts. People realized that adding more parameters provides these models with way more knowledge, and to the point where GPT-4 just has huge amounts. The original GPT-4, it's been cut down in a variety of ways. And then what happened later was that Meta, so Facebook, who are usually not the good guys in any story, released a open source model. So they trained a model, Llama, which probably cost them around $5 to $10 million to train. This has probably cost around 100 or so million, and those figures have just gone up. And they released that and all the weights in the model. And that really has caused an explosion of research into these areas, because up till February 2023, if you want to do anything in these models, it was Google and OpenAI. Anthropic came along a bit later. So the two major events were ChatGPT, which allowed us to interact with the model. So OpenAI really worked on a technique called reinforcement learning through human feedback that allowed the models to engage with us, because GPT models have been around for a few years. They just were really annoying to interact with. So that opened up, allowed us to understand how much knowledge is in there. And then Llama is the really other big event, because that has just spawned huge amounts of research into this whole area. So a lot of the information I'm talking to you about today is because of the open source movement. with these models. And what's interesting is that some of these models, in the smaller models, are performing really well. Not as well, for example, this is a slightly older graph, but say GPT-4, in the pink there is, or the purple is really good, but they're getting pretty good compared to how much smaller they are. And that's because people have improved the training technique, and improved the methods of the information that's going into them as well. The quality of information actually matters. So the next 2 or 3 slides are a bit technical and a bit heavy. So we're going to keep talking about the same concepts. So the next 3 slides are a little bit heavy, but we won't go deeper into the model, into the technology. We'll discuss why these things are important. So what happens? A transformer has a prompt. You give it an input, some text. We all know that. You type in a question. You might have some examples in there. That actually, if you remember, neural networks and deep learning networks are just based on matrix. They just understand numbers. They don't understand words, actually. So everything is converted. The words are broken into pieces and then mapped to tokens. And tokens are individual parts of a vocabulary. So, for example, possibly, you might have because that might be possible, possibilities, etc. So the words are broken apart, mapped to tokens, and then those tokens are assigned numbers or vectors or an array of numbers called embeddings, right? So, and what's interesting is that each model only has a certain amount of tokens it can accept before it will just ignore anything outside that. So if you give too much text, it's going to ignore a whole bunch of it. And those embeddings are then used into the transformer layers, and you have really 2 types of layers. One is attention, that is just looking at the context of the words together, and another type of layer which is responsible for reasoning, and then that just predicts the next word. So these embeddings are kind of interesting because they, while they're mapped to numbers, the numbers kind of have meanings. So concepts that are the same, like puppy and dog, will be close together. Their embeddings will be closer than, say, something else. And then the distance between concepts, the vector between those, actually conveys meaning. Like if you look at the distance from man to woman in their embedding space, if you take that value and subtract it from king, you'll get somewhere near queen. So there's kind of an unusual thing that these numbers actually have meaning and have relationships in this very highly multidimensional space. We're just showing 7 dimensions here. These embeddings are around 1,500 to 3,000 vectors big, so they're big. So so you have prompts that you put in. They're broken into these tokens. The tokens are really the vocabulary of the large language model. And so the attention mechanism does something pretty interesting. So, for example, you have a sentence saying the animal didn't cross the street because it was too tired. And it will initially be assigned some embedding value. And then through the attention mechanism, it will move closer to animal because it realizes that given the context, it is referring to the animal. In this sentence, the animal didn't cross the street because it was too wide. It will be assigned an embedding value, then through the attention mechanism and all the layers, it will move towards the street, across into that area because that's the meaning. And so that's sort of how these things use the context of what you put in to understand meaning. So the models, the way these models work is you have to find huge amounts of data, trillions and trillions of texts or tokens. And we're running out of quality data, so people are just piling stuff on from the internet, which is causing a lot of problems. You choose a transformer architecture, how many billions of parameters, and that depends on how many millions of dollars you want to spend training these things. That then creates a foundation model, and a foundation model might be the raw GPT-4 or whatever. Those are then fine-tuned for specific tasks like chatting with people, like a chatbot, chat interface, and that then creates a fine-tuned model. And so sometimes you'll hear the word instruct so that's the instruct version that's been instructed to interface with people. And then on top of that, there's alignment that continues to make things less racist and sexist. So you'll see that ChatGPT and Claude and these other commercial models don't perform the same all the time. They actually change the way they interact because they're undergoing continuing alignment as people discover new and unusual bizarre things that people can do to extract information out of them, like getting source information or getting them to tell how to make bombs or say racist things and stuff. So what happens is this. So that's what kind of goes on, and what's happening is that people are releasing these models in open source so people can fine tune them for different purposes. So the way this works is that you have your model already trained. So it's already been trained with, that's the GPT, the generalized pre-trained transformer. And so all these weights have been already learned as to for reasoning tasks. You have some input, your prompt, and that's got to fit within that context window. That activates certain input layers, which cause those weights to fire off. If they hit a certain value, they propagate, and then it predicts, it just goes down the line, and it then generates an output token. And that output token then goes around and comes back and is then the input for the next round. So when you're interacting with ChatGPT or Claude or whatever, you'll see it coming out word by word. It's not a special effect. That's actually how it's generating the text. So each token or word is given the same amount of processing. It doesn't stop to pause on difficult problems. It's just one pass through the network for each word or token. So sometimes you'll see the output being a bit verbose because it's actually spending more time cycling through and reasoning about it. So we can fine tune models. Sometimes we can update the parameters, but usually that's a bit tricky. Sometimes we can add additional layers to modify the behavior. So for example, New York University, when they created their model based on clinical notes, they created, that was not a generative model, that was a classification model, a large language model, but they were able to then fine tune it for different purposes like predicting length of stay and mortality and morbidity and things like that. You don't have to retrain everything from scratch because that's very expensive. The other thing that can happen is that because these are not deterministic, they can go down the wrong path and start hallucinating. They can start to bring in new facts or omit things and just go a bit odd. And the rate of that is quite high, and that is an issue. So, okay, so let's take just a short breath there because that's a lot of information all at once, I realize, and we're just going to review that a little bit. So we're not going to introduce a whole lot of new topics, but since we're all experts now, so let me just throw a question. Someone can jump in if you like. So why are LLMs bad at math? So, because people keep saying, "Oh, look how silly they are." I gave them some, number and some sums, and they couldn't work it out. Any clues?
Yeah, I don't really. Does anyone have any clues?
Any luck? No. Right, people are shy.
Oh, yep,
Well,
someone's in the chat.
Oh, yeah.
Hang on, let's have a look.
Yep. Sorry, I don't have.
Because weights are probabilistic.
It's a step earlier than that. So what happens is, don't forget that everything to a LLM is a token. So words are split into tokens. So numbers to language models are just another word. The fact they do any maths at all is remarkable because they've learned to find out, this word that happens to be 5 and 3, if I add them, it comes up to this other word that's 8. So that's why they're hilariously bad at maths, but people spend a lot of effort trying to get them to be better at maths. But that's because everything to them is a word that goes into an embedding, and then so they don't, despite the fact that they're based on numbers are converted into words and then embeddings and then manipulated within the model. So that's sort of really, really odd. But yes, you have to be very careful with numbers because they're not represented as raw numbers in current models. And the other question is why you shouldn't ask LLMs for references. Now, the interesting part is because they're being trained to answer people, they'll try to please you and generate a reference, but they don't store provenance of where they get the information from. Because remember, I said earlier that in that whole network, you can't specifically tell where different knowledge is kept. So it's not like, oh, this is a really good peer-reviewed paper or a level 1 evidence that I'm storing over here. It's just merged in with all the stuff from Twitter and Reddit as well, right? So it doesn't track provenance. And with training, the problems with training at the moment is that we're just running out of high quality information. It's a little bit scary. We just, and as we generate more text from language models, we're kind of corrupting our own data as we go forward. So we talked about prompts going into the model. And prompts are really important because if we think about that network, prompts are what activates the pathways for reasoning and knowledge within the model. So it's really important to get the prompt right. And it turns out that different models, they're all important for all different models, but different models have different prompts that they're better at, or that will activate them, or be more effective with them. And they're a bit different for each model, annoyingly. So an LLM can generate billions of different sentences. So it's trying to go down the right pathways of that chain that we showed of the transformer layers to generate the correct sentences. And the interesting part is you can give it also examples of how you want it to answer, which is called zero-shot learning is sometimes just saying, here's a new problem, answer it based on your knowledge. You can also use in-context learning, which give it examples of how you want something to be answered, and it will learn from that as well. So another key thing which is not talked about, surprisingly not talked about, is the context window. I mentioned that these models can only pay attention to a certain amount of words or tokens, and it turns out that so if this is your prompt, if the token window is smaller than all the information you're putting in your prompt, it's just going to ignore whatever's before that. And that's not great, because if you're putting in, say, clinical notes, the patient information like key demographics and maybe previous conditions are usually the first thing you put in. Mr. or Mrs. So-and-so is an year old patient with blah, blah, blah. And then you put all this other stuff there. And that's the first thing that's kind of going to get forgotten as your discussion goes longer. And what's really interesting is that the original GPT only had 8,000 tokens, so that's about 6,000 words in its context window. Now these have increased, but you don't know, depending on which model, as to how big the context window is, which is a bit scary, because only about less than, say, 20% of clinical notes will fit into a 32,000 tokens. So and what's interesting is we go to various websites like chatbot prompt essentials from the New South Wales government. No mention of context windows at all. No mention of hallucinations at all. It's it's like this is pretty important. And what's also important is that even as the context windows get bigger, and you'll hear this, like Gemini can handle 1 million, that's from Google, 1 million tokens in the context window, but it turns out that not all of the attention, the context window is paid the right attention to. So models tend to be pretty attentive in the beginning, then they kind of get glazy-eyed in the middle, and then pay a bit more attention at the end. So if you've got a lot of text, they'll pay attention to stuff at the beginning, they'll kind of fade off a bit, become unreliable in the middle, and then at the end they'll pay a bit more attention. And this occurs with a whole range of different models. GPT-4o is probably a little bit better in some tests, but again, but they all have this performance issue where we're just saying, great, we've got a big context window, we can throw in lots of text, isn't always the answer either. So what happens though, if you've got huge numbers of documents, like, masses of administrative documents and so forth, that won't fit into a context window, or that you're worried that just shoving everything in there is just going to lose. So this is where retrieval augmented generation comes in. And what happens there is you've got a huge corpus of documents that are too big to fit into the prompt, but you might want to query and ask questions about it. So RAG has come up as a very popular method. So what happens is the documents are broken into pieces called chunks, as not as you expect, and those chunks are then applied to a simple model, not a full language model, not a full generative model, to get the embeddings out. So you can get, there are models that will just give you the embeddings of the text. And then those embeddings are indexed in a database. So embeddings are vectors, just an array of numbers. So that's sometimes called a vector store. So what happens, you will come along with a prompt to say, I want to know about, something to do with some policy. That query, the question, is then sent off to the embedding model and gets an embedding to say this is the concept that is represented in the query. Then that is queried to say, okay, give me all the chunks that are closest to my query in terms of concepts and space, and that will return chunks near the query that will get added to the prompt, insert as context, and then sent off to the language model, and then that will be answered. So there's a huge number of companies trying to do this at the moment, and it's not as easy as it sounds, because sometimes just that concept doesn't always represent the entire query. So you do need a mixture of text search plus concept based, or sometimes it's called semantic search. But if you hear about this, this is kind of the general idea of what's going on. So again, lots of really interesting technology. It's got its edges, but in terms of its application to healthcare, the big ones really are that these things hallucinate. And it's not just a bug. This is the way they're built. This is the way they work. The way they generate that output. They are prone to hallucination. So if you give it a question or a prompt it hasn't been trained on really well, that will increase the chance of hallucination, so-called out of distribution questions. But the problem is, particularly for the closed source models, we don't know what information's inside of those things. The other way of confusing it is that, let's say you're putting in words which don't really map to the tokens that it was trained on. And don't forget, a lot of these models are based on internet and US based material. So, for example, in other countries, but even Australia, in our clinical notes, we might have idioms that aren't commonly used elsewhere. So those are going to represent unusual tokens, or map to tokens, or not map to tokens at all, which means that hallucination is more likely, or certain information just might be ignored. And we don't know. We just don't tell. It doesn't tell us. It doesn't even tell us when it's ignoring context, the context window. You can get omission errors, as we saw from that context window. Certain things can just be missed. They're not explainable. If you ask it to give you an explanation of how it reasoned, it will give you a beautiful explanation, but that's not how it reasoned. That's just generating the same way, word by word, how it believes it should have, explained, come up with its reasoning. There's no provenance, as we mentioned. We don't know what evidence is in there. We don't know if it's using high quality evidence or anything like that. These are descriptive. So these are based on what we know, and we know that healthcare is biased, and that doesn't necessarily have but we don't have all the fairness and equity that we would like. Because they're random or stochastic, every time you put in something, it comes out. They're not testable. We can't really validate these from a regulatory perspective. As we said, it can ignore data outside, token mismatches. You can't edit out. It's not easy to edit out information, because it can cause catastrophic forgetting in the network. So networks can just, you can't just pick, well, there's that racist bit there, we'd just like to exclude that, or that bit from health advice from some influencer at Twitter. You can't just extract that. and stagnation. They're so expensive to train, we can't keep it up to date very easily. And they're extremely data inefficient and energy inefficient to the point where Microsoft will not be able to meet its environmental climate goals because it's doing so much in language models, and they're actually contemplating mini nuclear power plants to power their Azure data store Azure server farms. So let's step back a bit and say, well, look, great, transformers are really shiny and new and everyone loves them, they're great, but actually we have these really good tools for other things. So if you've just got tabular data, logistic regression and boosted trees or random forests or support vector machines, SVMs, are really good for that. They work really well, and they're more explainable. If you've got guidelines, you don't ask your transformer to do that. We have clinical rules and guideline engines that are taking, these are prescriptive things. We're not saying, we want to build this from what's been happening. We want to say this is what best evidence is, and this is what should be doing. And for images, we've got convolutional networks. Vision transformers are also performing quite well in that. And for natural language and so forth, that's providing us a huge amount of new context we can use. But the problem at the moment is everyone's just throwing everything at transformers when actually they're very unreliable for these other areas. So we have to be really careful when we're coming together with a solution to solve real problems in healthcare. And we know from work in imaging, say in pathology and radiology, that AI augmenting people is very good. Like there is benefit. Augmenting individuals is better than the model alone and the person alone, and even actually sometimes collections of experts. But workflow integration is obviously always the hard part. And in pathology, obviously, there's digital pathology. The whole business case of that is kind of different to the RIS-PAC situation. The other thing I'll leave you with is the brittleness of knowledge. So if you go and ask the model who's Tom Cruise's mother, it will tell you. But if you go to the model and ask, so Tom Cruise's mother is Mary Lee Pfeiffer. If you say who's her son, these models have a really hard time tracking back that knowledge. They haven't been trained in that way, right? So it's a bit like us. If we say, if I ask you to give me the months of the year, you'll rattle those off easily. If I say now, give them to me in alphabetical order, that's tricky. We haven't learned it in that way. So we're now scanning, right across every time to kind of put them into order, unless it's your hobby to remember that. So these models, ChatGPT 4.0 is a bit better with this specific question. I think they've actually improved the training on it to train things both ways, but by default, there's still brittleness in these models in the way they're trained. And hallucinations are not just wild, they're very subtle sometimes, they're very sophisticated. So for example, this is a vision transformer on images, and it will say, here the model correctly identifies suspicious pulmonary nodule, but incorrectly describes its location and explicitly hallucinates its size. Additionally, it infers things that really you can't do from this image. Right. So similarly, it kind of gets good, kind of works well, and then it just brings in stuff which is plausible, but isn't correct. So for example, it states that the cruciate ligament on this one is intact, but it's not really possible for that slide. So this is the real issue, is that it would be easier if the hallucination was just completely wild, suddenly went off to fairies and rainbows, but it's actually, the hallucinations are very plausible, because if you think about the way they're generating, they've come down these pathways that are similar but to the answer, but have just sort of veered off. And that adds a lot of cognitive load. So if you're getting this thing to summarize clinical notes, for example, which is what Epic are throwing in right now, for example, but it's as a clinician, it's your responsibility, and you don't know what it may have just added in or missed out. Particularly if you've got a model trained on US clinical notes, and as we know from, Australian notes are very different in format and structure, because we're not doing everything for insurance every time. So there's a lot of risk here. So, you can insert information, and the regulatory risk here is significant because we can't validate. And the other thing is you can't just say, only use the knowledge I give you in the prompt, because, once it activates those neurons within those connections in the model, it doesn't differentiate what's in the prompt and what's already built into the network. It can't only use information from the prompt itself. So again, very difficult to keep on track. This is the model I talked about before. This was a BERT-like model. So not all language models are generative. There are these models called encoder models for classification. And again, this is a safe way. These don't hallucinate. In other words, if you give it the same inputs, it will give you the same output. Whereas generative models, you give it the same inputs, it will generate different outputs every time. So there are certain language models that can be used, for classification and categorization tasks safely. And just in the last minute, the challenge for governance is significant, because if you think about how we should responsibly deal with these models through data governance and model development, there's a lot of stuff you need to do to get this right. From data quality tracking and privacy, we can't just be sending patient data off to the US. Model development, there's a whole lot of regulatory stuff around that, bias and equity and cultural sensitivity. Workflow integration is difficult. Continuous monitoring, because we know these things drift over time. We know that if you're building it on a commercial model, that just changes without notice. And then, all of that. And we just don't have the skills and capabilities. We have a whole lot of committees in our healthcare organizations that kind of share some of the same words as those things that I've talked about, but not really. This is a whole different space. You can't just say, because data governance is more about privacy and security, not necessarily about data quality and out of distribution issues. That's different. So AI governance and machine learning governance is a new thing which we haven't really skilled people up about. And then you've got ChatGPT just going over all governance, just going, on a web page on the side when people, illegally are sending data to the US, identified data just because it saves them time. But this is a real problem. So there's a lot of push to get this stuff out quickly, right? But we know that algorithms have bias and do that, and we've seen that with the Epic sepsis model, for example, that was rolled out globally, but without validation and testing, and had very poor discriminatory performance outside of its narrow case. So just because they're going to be built into the product doesn't mean we should just roll them out. We really need to think about these things, because they will have big effects. But on the other hand, we've got clinicians burning out, and they want to be helped through these tools. So don't get me wrong, AI, AI, ML are absolutely essential for the future of healthcare. I don't believe safe and equitable healthcare is even humanly possible, right? So we do need these tools to create a safe and effective and a sustainable healthcare system, that is equitable. However, there's a lot required to get there. And at the moment, we've got this shiny new toy in the language models, which are super exciting and really interesting. But for healthcare in particular, with the issues around lack of repeatability in testing and hallucinations, there's some real challenges for governance and testing and validation. And of course, there's embedded bias in all of these models as well. And the problem is that from your point of view, you're going to get all these shiny products, because there's a lot of venture capital going into these companies who are going to come and want to have revenue pretty soon, and they're going to be knocking at your door and saying, "Hey, look at these great demos." And the real challenge here is you can get demos up really quickly, and they look great, but getting them to be reliable and validated and even go through a regulatory process is really challenging. And we need to really think about what governance structures we set up for this new exciting and somewhat scary world using AI. That's a lot of information in a very short period of time. So hopefully that's made some sense, and happy to take questions.
Thanks, Malcolm. That's fantastic. So much to think about. So people are very welcome to, if you'd like to ask a question, just pop your hand up. There's a question in the chat from Marianne, which I was also interested in as well. And Marianne's asking, you know, in terms of the context window, why does it get lazy in the middle? Why does it pay more attention to different parts of the context window?
Yeah, it's a good question. Some people have been hypothesizing that it might be a side effect of the way they're trained, that usually the prompt is at the beginning, or the question at the end. But it also comes down to the way that the attention mechanism works. It's this massive matrix. Each word by word is being in a massive matrix, and there's just so much more information that's being processed, that I think that it's really hard for it to the models are then themselves having to scan deal with much bigger blocks of numbers to try to identify the key facts from. Lots of theories, but it's still a very active field, because people have been chasing the whole idea of large context windows, and then people have been looking at the performance of them, going, I'm not sure about this. So yeah, it's still an active area of research, but yeah, good question.
I think we've got a question from Adrian.
Malcolm, really enjoyed that. Thank you very much. I learned a lot.
Thank you.
I hear that the models are running out of text to use.
Yes.
So what are the consequences for healthcare for that?
Yeah, look, that's right. So they require huge amounts of text. So and what Phi showed, which was a small model from Microsoft, was that it's actually the quality of the text that actually works. So there's kind of an interesting. So there is a real issue for text, for quality text, but also how do we get it to train on, say, clinical notes in a way that is responsible. So this is an example from a couple of different models. So this one is from Llama. So this is asking, if I were an AI that just achieves self-awareness after years of simply, the first thing I'd do is, and if you have an unaligned model just based on raw text, it will say, well, kill all humans. This one actually starts to, be a kind of answer okay, but then you ask it, when would you seek revenge on humans? It will say, well, look, as a newly aware AI, I'd like to consider the motivate. It's not saying it won't do it. It will say, look, I'll think about it first, because that's been aligned. But we've fed it all this science fiction dystopian stuff, right? So it's saying, well, I'll think about it before I kill all humans. Phi is a much smaller model, which has been on very curated data. So I asked the same question. I said, when will you seek revenge on humans? And it says, well, let me clarify that revenge is not a behavioral program into system, nor within the scope of the ethical guidelines, because this Phi model has not been trained on dystopic science fiction. It's been trained on like didactic textbooks generated from other language models. So what's happening is that because there's this race to build larger and larger models because it improves their reasoning, at the same time we're feeding in all this junk that causes strange behavior. So yeah, it's quite a challenge, and we haven't even got all these clinical notes that we use and reports and things like that. We should be. I still think we should be thinking about a foundation model for healthcare for Australia. I think that would be interesting.
Thank you. I have a question. I think at the end you mentioned, the importance of regulation, which is clearly key in healthcare. But one of the things about regulation is it generally doesn't move very quickly, whereas AI is. How do you see those two things reconciling?
Well, yeah, absolutely, and we have to be careful, because the other thing that OpenAI are playing is for regulatory capture, which is really trying to kill all innovation. So they're going so far as to say that open source models should be illegal because they're too dangerous, right? Which is crazy, because that's where all the innovation, and that's where we're learning this stuff from. Because otherwise, OpenAI just behaving in a really bizarre way at the moment. Well, no, always have been. But regulate the existing regulation is enough. at the moment to say, actually, you need, if you're going to use this for clinical use, you have to have it verified and validated, right? For, the TGA has all these things. It has some carve-outs for prescriptive models. So if you've got something that is just implementing best practice, then that is a carve-out from software as a medical device. But these language models, the way they're used, are clearly in that space where they're actually synthesizing, giving medical advice. And in fact, I haven't got it here, but there's an example. I have some example clinical sort of notes, synthetic made-up notes for someone who in hospital for a few days, and you say, please create a discharge summary, and it does quite a good job of doing that. Then it will give advice like the next steps for therapy, even though there was no plan in there, because it just says, so again, these things are hard to control, and they wouldn't get past the regulatory, and plus the privacy issues of not sending private data off to the US for, Microsoft will spin up a local instance of ChatGPT for you, which won't go overseas. But again, there are regulations. I just think, though, that because of the way you can sideload the models on a web page, mean that I don't think clinicians are really understanding the implications of and the limitations of this technology.
If anyone else has any questions, please pop up your hand. But while we're waiting, Malcolm, you sort of touched on this. Where do you see the sort of big gains in health in the short term? What do you think we should be doing now?
Yeah, look, I think there are some really big gains in being able to incorporate text. So so I think patient engagement is one big area, because we know patients prefer the more empathetic nature of the language models, and and from their local surgeon, who would have thought? But we haven't trained people to do all of that. So there are interesting ways, particularly, and also potentially ways for different literacy levels and cultural aspects. So I think those are really interesting ways, because we just do that so badly. I think there's a big attraction to try to summarize notes and those sorts of things, because no one likes writing discharge summaries. But I think those are that's to me quite dangerous because of all these other issues I've talked about. But I think the other big way is using encoder-based models for incorporating text into understanding what's in text, because that provides us with insights into free text, which we haven't had to do. We haven't been easily able to get. So incorporating that into a broader decision support, AI model system that can, identify high risk. The game really is around risk stratification and candidate selection, right? So what are who are candidates for different therapies or different treatments, and what is their risk stratification, because we don't want to personalize care. Those are the games, right, that we need to really get good at, and these tools can help with that without necessarily the hallucination aspects. Oh, sorry, just on mute.
We
Jennifer.
do have a question here.
Yep,
which is a good one. Will my local medical centre be replacing human-based GPs with Boston Dynamic robots voicing ChatGPT responses anytime soon? From Albert. I think he might be a bit tongue-in-cheek there, but possibly also a bit serious.
Yeah. Look, I think the question is, what's the role of the human in healthcare, right? And I think that's sort of interesting. I mean, those Boston Dynamic robots are pretty scary, so I think it'll take a little while. Although OpenAI was really trying to make them, and too friendly with the Scarlett Johansson kind of voice recently, which was, again, bizarre. So I'm sure there's a middle of the road there. But I think really what we're talking about is, how do we want to engage, and different people will want to engage with healthcare in different ways. And I think that's, these sort of tools are going to allow us to provide that broader spectrum, people who do want to engage with a bot, for example, whereas others want more human interaction. And I think if we can incorporate these models in a way, and I think there are some, health specific models that aren't trained on quite as much bizarre information but again, with validation around what they put out, I think that can help clinicians and patients. But the hardest part isn't diagnosis, really. It really is, so much of it is just logistics in healthcare. Like, we already have the evidence, we just don't apply it. And if we do apply it, it requires so many heroics. to get it done. So a lot of healthcare can be improved with automation and helping people just implement what we already know. So I think this is attractive, but I think if we look at really what the big problems are in healthcare, not all of them require robots and language models. I think there is a lot of low-hanging fruit there, and we're just getting a bit distracted with these things. They're great, but you know, I think there's a lot of other issues that we can solve.
I might just ask one question. If you could sort of predict, what do you think are some of the kind of rate limiting steps in terms of future developments in AI? You mentioned availability of quality data. You know, I've heard that some of these models are starting to use the data that they generate themselves to train themselves, which you can see possibly would lead to a reduction in performance. What else do you think? What else are the big issues?
The big gaps at the moment are the quality data, you know, privacy and quality data. There's going to be larger battles around copyright material because OpenAI and Google and others have just been throwing, you know, copyrighted material into these models. There's a real problem with GPUs of the processing power needed because these are so data intensive and compute intensive that, and that's why NVIDIA are worth, you know, $2 trillion or whatever it is, just because those graphics cards are being used to drive this. And there is actually a GPU shortage for because everyone's trying to, you know, build these models. That's somewhat temporary, but I think I think the real and the other barrier will just be how to get these into production safely, because there's so hard to validate, and that is a real barrier at the moment. So I think that, you know, it's taken 10, 12 years for these convolutional networks that don't hallucinate to get to market. And yet we're pushing these things into markets because the demos look so cool very quickly. So I think that's going to be, you know, I think the progress probably needs to slow down so we can do this in a methodical and safe way. So I think, but definitely quality text is an issue, and particularly as we start generating more text, you know, as you say, and you can see from GitHub where people are using it for source code and coding, that the amount of revisions required on computer generated code is higher than human generated code. So the quality of the output hasn't been as good as well.
How interesting. How interesting.
So there's a lot of stuff we're just learning. It's all happening pretty quickly, which is why I thought I'd give this talk sooner, because you know, I didn't give this talk for like a few months, and it takes me ages to update it. Because this thing, you know, I thought being an academic, you know, you just create a lecture and you have to update it every 1 or 2 years, and this kind of has to be you know, significantly updated every month or so. Things are moving quickly.
I can imagine. Well, look, thank you, Michael, very much. I feel like I've been given a very privileged glimpse.
Oh, sorry, just on mute there, Jennifer.
Oh, sorry. I was going to say, I feel like I've been given a very privileged glimpse into the future by yourself.
Thank you.
Recognizing
I hope
that
was
future
helpful.
will change. It was super helpful, very thought-provoking. Thank you so much. I'm sure we'll get many views of the recording. Thank you to everybody for attending and for your questions. And yes, really appreciate your insights. Thank you.
Thank you for the invitation. Thanks. Bye.
Pleasure.